Well, welcome back. We're going to talk more today about the gas condensate blockage, and uh, we're going to make use of kind of what we've already talked about, review some of that using the e-note on condensate blockage, which is pretty much just a summary of what we've already talked about, and then in this e-note called GC rate. We're actually going to look in more detail at the calculation procedures for doing the entire A to Z calculation of the pseudo pressure at a given point in time within a model. So you actually we work through an example that is essentially what's going on in every well grid connection, every time step to calculate this area under the curve of the mobility. So that's going to be just to review the calculation process. So we did part of that yesterday, just calculating the range of KRG, KRO for a given well, and at a given producing CGR. And then I'm going to let that be more like a self-study. It'll take almost half a day to actually go through and do this exercise together. So we're going to go through the calculations. The solution is, so to speak, given in that e-note and the files related to that. But if you really want to understand that calculation process, then I would recommend reproducing the same calculations, but using a different time from the reservoir simulation. And we'll kind of talk about how to go about doing that. So if you're really interested in trying to understand the calculation procedures, the details of exactly what's going on, this is kind of on your back, and it gives you the way to go about doing that. And then we're going to move into the relative permeability discussion. I'm going to make some comments about the endpoint saturations that are a bit contradictory to what I said yesterday and been saying for many years, so we'll look at that briefly. I'll give you an example of a Corey-type rel-perm equation that's used in the reservoir simulator sensor called KR Analytical, and we'll study how the endpoints affect this fundamental relationship between KRG and the ratio KG-KO. Then I'm going to go through a what I call a 3-core thought experiment. We'll come back to that. Basically, it's to show you what's similar and what's different about the flowing well stream. Let's say 3 meters within a well. You know, the first meter, the second meter, and third meter. If just purely the permeability and rock is changing for the three different intervals, but you're flowing essentially the same identical fluid through each interval, albeit at different rates. Same pressure drop, same fluid flowing through the rocks with a same, everything is the same except the flow rate. So how would the blockage be in each of those meters? One with 1 millidarcy, one with 10 millidarcy, one with 100 millidarcy. So what would be different in the 3 pieces of core? And then I'm going to give a presentation. This paper here is basically giving the results from the 2-year joint industry project. There's a companion paper that was presented at the SCA. I think that's the Society of Core Analysts. It's more on the detail of the laboratory procedures that we developed and tested as part of that JIP, and those are the same procedures pretty much being used today by Stratum as a continuation of what was developed by ResLab and then Weatherford. And that presentation also ties the the measurement, the application, the development of a correction to the relative permeability for capillary number. So we bring in that capillary number in some detail, and we try to quantify how the capillary number improvement will actually have a bottom line impact on well productivity. So that's a very comprehensive, nice paper that puts together the effect of the rock relative permeability behavior on the well modeling. And then after lunch, we're gonna have a presentation with Kameshwar Singh. He's put together 2 presentations. He usually comes in and does this. We'll do maybe the first one jointly, and the last one he'll take over the reins on. The first is basically to give a complete A to Z workflow of how the company deals with condensate blockage for any new project. That workflow, I think, is general and can be used by anybody. It doesn't need to be us. Answering the question, is condensate blockage important for my field or not? And if it is important, how to go about designing and preparing for getting laboratory relative permeability data, interpreting that data, and then applying that data in your modeling. That rolls over into the last topic. Singh will take is the specific implementation of this pseudopressure option in the Schlumberger software Eclipse 100 and 300. So that's kind of the game plan for today. Are there any questions from yesterday or the earlier in the week that we want to try to take before we kind of get started on the new material? Any questions out there? Okay, so we're recording, we're projecting. I haven't heard anybody out there say good morning, Curtis. I don't know if you're out there. I don't know if you.
Good morning.
Good morning. Thank you. And you have to do the Curtis. Yeah, thank you. Good morning. All right. And I get bored of these human beings in the room with me here. You know, that hurts, but it is what it is. Okay. So the first item is that this equation we looked at yesterday for calculating KRG, KRO as a function of pressure, and it's from the wellbore pressure, wellbore flowing pressure out to what we call P star, and P star is the dew point of the well stream. Okay, with known producing oil gas ratio, which is what you would need to go into the black oil PVT table and find out what's the dew point of that producing oil gas ratio, or it's the well stream composition if you're using an EOS based simulation or modeling of the PVT. You basically take the well stream composition, go to the equation of state, calculate the dew point, and that's your P star. So within the range from any flowing bottom hole pressure up to the P star, we can calculate what actually will be in every grid cell. So if you got 100 layers, you can go to any layer at a given time. If all the layers are producing the same well stream, they'll all have basically similar pressures if they're communicating vertically. They're not different reservoir flow units. So you can go to any of those layers, go into any of the cells in what we call region 1, and all you need to know is the pressure in that cell and the producing CGR of the well, and you can actually calculate the ratio KRG to KRO in that cell. You don't need to know nothing about the relative permeability at all. Just the producing GOR of the well, the PVT model, and the pressure of the grid cell. It could be 30,000 grid cells in that region, and all these layers and 100 feet out. In that region 1, every grid cell we can go in and calculate the ratio KRG to KRO, knowing nothing about relative permeability at all. And that equation, and it doesn't sound right. I agree. It doesn't sound right. You know nothing about the relative permeability, but you know the KRG, KRO. And this equation that we looked at yesterday was, I'll try to put it in black oil, in terms of black oil, was something like this. We had the units thing, 1 minus R little rs times RP. I think this was the first term. And then it was mu was the gas on top, oil on top, I think, mu OBO, mu G, BG, and we like that. I think that's right. No. That's not right. Basically, I know that the KRG needs to have the mu G, so that needs to be mu G, BGD. Is this correct, what we used yesterday? Okay, I think so. So we've got the PVT properties, and then we've got the producing PVT property as a function of pressure. That's the RS, little rs, mu, and B. And then the producing PR, that's this 1 over RP. Okay, so that's all you need to find that ratio. So I wanted to kind of like, where does this magical equation come from? I just wanted to kind of to try to get derivation for that. Now, what I'm going to do is I'm going to leave, because of all the units and the black oil, blah blah blah, all these things. I'm going to try to do it in kind of a generic way, and then we'll come up with the equation that we would use in the case of using an equation of state, for example, or a laboratory PVT cell. So what we're going to say is that in the steady state, this applies in the steady state flow region. Where the flowing composition remains constant, or the flowing, the flowing gas-oil ratio, or the flowing oil-gas ratio would be constant, and it would be equal to the well stream, producing well stream composition at a given time. And in order for that to happen, if we take the well stream composition, that's equal to the flowing gas composition, right? Leaving region 2, entering region 1. So Y is gas, so I don't need that. So basically, so this is the gas composition. I'll basically say region 2 out. It's leaving region 2. So that composition, and that's our producing well stream composition at entering the wellbore. Now, if we just took this to the laboratory, if we just took that well stream composition to the PVT lab, right? and we did a constant composition expansion test. So what would we get if we look at, well, what we'd get is that we'd see that as a function of pressure, that would have a dew point, right? Somewhere. And then we're going to plot what I call VRO. We're going to plot the oil volume over the total volume, which is the same as the oil volume over the gas plus the oil volume. Okay, that'll typically go from, even for rich condensates, 0 to 20%, for example. I'll just take an example. And this curve will actually have kind of like almost like a normal distribution shape. That looks terrible. It looks something like that. And what's common at each point on this curve is that the total composition is the same, right? So, because what we're saying is that throughout the entire steady state flow region, that the flowing composition, if we could just go in and sample the flowing composition, that would be equal to what's in the PVT cell. So whatever pressure we're at between PWF, which might be here, okay, PWF or some higher pressure, and then out to, and remember this PD of the well stream, that's what we define as P star. So anywhere within this region 1, the flowing composition is represented by what we have in the PVT cell. And accordingly, the ratio of the oil volume to the gas plus oil volume, not in the pores, but of the mixture flowing, okay? Okay, of the mixture flowing, because now we're only talking about the mixture, the flowing mixture composition, not the pore composition. Okay, so in order for that, if we took a sample of what was flowing, we'd say, oh, part of that flowing mixture is an oil volume flowing at a certain rate, QO. Some of it's a gas volume flowing, and so basically the requirement is that of the flowing mixture, and of course these are the rates of the flowing mixture, this ratio needs to correspond to this constant composition, which is the flowing composition, throughout this region 1. So this is the criterion. In other words, if we've got the flowing composition and we flashed it down, then we would need these rates, okay, because the volume is just simply QO times an incremental 1 second delta T, right, to get the volume at a given point within the region 1. So that's basically delta T, some small delta T, and delta T. That gives you those volumes at a given point in region 1, and for that flowing mixture. So this QO over QG plus QO locally within the region 1 needs to be given by what's seen in the laboratory CCE test. Okay, so that's the requirement. Now the question is, what is QO and QG? So QG is basically KRG. This is mu GB. We're not talking about surface rates. We're talking about local reservoir rates. So this is not is not QG hat. It's not a surface rate. And QO is basically KRO mu O. I don't know what I wrote B here for. QG. And of course, this has got area, length, delta P, area, delta P, length, to get a volumetric rate. But then these are going to cancel out. This part here is going to cancel out from the top and the bottom.
Also the absolute permeability.
Yeah, and the absolute permeability should be in here. Like that. Thanks. And so what we end up with is that the QO over QO plus QG is the same as the relative oil volume from the CCE test of the well stream mixture at a particular pressure. But that's equal to KRO over mu O divided by KRO mu O plus KRG mu G okay. And we can just turn this upside down to make the algebra a little bit easier. Okay, KRG, UG, plus KRO, UO, KRO, UO. And then we divide through by 1 over KRO mu.
Leave it up.
1 over KRO mu. That. So that ends up being KRG over KRO mu O mu G plus 1 over 1, right? So then we can bring the 1 over the other side, 1 over VRO CCE minus 1 is equal to KRG, KRO, UO mu G. And then we can just rewrite this as KRG, KRO is equal to 1 minus VRO, CCE, minus 1, mu G, mu O, and that's the equation. And we can compare that with the black oil version. We'll take a copy of that down here. Black oil version. That's representing the same thing. Which means that, basically this, you can rewrite that as RP minus RS, 1 minus little rs, RP times BGD over BO times mu G over mu O. So this term here is the same as this. So that term there represents 1 over VRO minus 1. So that term is giving you what fraction is oil, what fraction is gas indirectly. That's what that's giving you. So if you have a compositional model, in order to compute this entire term here, KRG at a given pressure, you just do a CCE flash. You take the VRO, you got the gas and oil viscosity, and bang, we've got the same numbers we calculated yesterday. But instead of using RP, we're using, instead of RP, we're using well stream composition with the EOS, okay, to get VRO, mu G, and mu O. So we're using the same kind of information. We need the RP. So you'll find this in most of the publications that we have. We'll have both equations, one for a black oil formulation, one for a compositional formulation. And probably the most confusing thing about this is that when you find the KRG KRO, okay, when we find the KRG KRO, and then we go to the relative permeability curve, right? The table that we have, like we did yesterday. So we've got KRG, KRO as a function of pressure, okay? And then we go to the KRG, KRO from the rel perm table, right, that we're using. We also have the KRG, with the KRO, and we have, for example, oil saturation or gas saturation. So we have these from the rel perm table. So we go from here to here, we get the KRG, we get the KRO, and we also get an oil saturation, right? That oil saturation has nothing to do with VRO. Nothing. If there was no water saturation in the core, then VRO would be the same as oil saturation, right? Okay, if there was no water in the system, just to make it easy. So, but there is no relation to VRO and SO. This has nothing, this oil saturation here has nothing to do with the VRO calculated from the CCE. Nothing. What you'll see is that, you know, you're down here, your VRO might be 0.04. I think we made some calculations. It was down low like that, right? But if you go to if you went through that exercise, which is part of what we'll look at today, if you went through that exercise in the rel perm table, you'd find a KRG and a KRO, and you'd find an oil saturation, and that is not equal to, so the SO is not equal to, that's not right, to VRO divided by 1 minus SW. Or is it times? Should be times. SO, yeah, I think times. That would normally, you would normally think. So the VRO is the relative oil volume of the flowing gas plus oil, not the pore gas plus oil. Okay, the saturation of oil is always going to be greater than this term here, and it could be much larger. So they have nothing to do with each other. It's confusing, but it is what it is. So you're probably confused. Okay, it's a confusing thing. Any questions about this? The point is that this fundamental relationship of why you can go and If it's a steady state flow region, meaning that there's no accumulation going on in that grid cell at this given time and thereafter probably, there's no accumulation or vapors, there's no net change in stock tank barrels, you're not losing any stock tank barrels as you flow, then this is the relationship that gives you the ratio Kg/Ko. The model will have to adjust its saturation to get a KRG and a KRO that satisfies this equation. And there's only one saturation that it can get to get that. Okay, any questions or comments or thoughts? I'll put it another way, that the composition, if you look at the composition in the pore at any given place, right? This is going to be totally different than this flowing composition. Okay? The pore composition is going to be totally different than the flowing composition. If we could go in and collect the pore composition and we did a CCE and we got the VRO at a particular pressure, okay, and then we took the flowing composition and we did the CCE and we got a VRO there like that. So this is for the flowing fluid, this is for the pore fluid. These are not going to be equal as this, okay, they're not going to be the same. And this is always going to be greater than, because you have two-phase flow in the region 1, therefore it's going to be greater than the critical oil saturation. It's definitely going to be greater. The pore composition is going to be a richer composition than the flowing composition. And I've always had, I remember myself trying to learn this stuff early on. I've always had difficulty in understanding kind of that, So let's look at a pipe analogy. Let's say that we're flowing along the bottom of the ocean, the pipe. We've got this pipeline. And what we're flowing through here is a gas of a certain composition. Okay? And what goes in is what comes out. Okay? And let's say for practical purposes, the distance is such that there's no real pressure difference or anything. Okay? Y'all see this? So the flowing mixture is just a gas phase flowing through this pipe. But what you know is that there's very likely, because of this low spot, you're going to find some liquid here, some liquid condensate that's static. Okay? This is going to be, I don't know what you want to call this, liquid composition, but we'll just call it Xi. And Xi is in equilibrium with the flowing gas. Okay? So this is in equilibrium with the flowing gas, okay? And if you were to take a, if you were to take a segment of this pipe, then you clearly see that the composition in that segment of pipe is totally different than the flowing composition, right? And if you did a CCE of the total pipe composition, then you would get this liquid volume, gas volume distribution. But in this case, the flowing gas, if you did the CC of it at this pressure, it would be no liquid. It would be saturated. It would be at its dew point. Okay? So the composition in the pipe segment is not necessarily, now here it's the same thing. Here they're the same thing. But it doesn't necessarily, and it certainly won't in this low spot, be equal to the flowing gas composition. It's the same kind of analogy as what's going on in region 1. Same kind of analogy. Okay. I'm just saying there's no pressure drop. It's just to make it simple. I mean, okay. Yeah. So that was kind of something that I know I myself struggled for a long time with this concept and this issue, and you know what's going on, and so that's why maybe you guys are struggling. I don't know, maybe not. Okay. It reminds me of when I was trying to learn all of these technologies of Mike Petkovich, you know, the gas well deliverability paper, it's in there, you know, the material balance paper, high pressure, you know, I had a life of, you know, 20, 25 years trying to learn all these technologies, layer no crossflow, and I'm a slow learner. And I remember him being so upset. You know, we'd be talking about something and I'd be asking the same question the third or the fourth or the fifth time. And he says, Whitson, you figure it out yourself. It's right. You know, he just gave up on me. Okay. And it was just like all sorts of topics. And, you know, maybe I finally got it, hopefully in most of the situations. But you know, he just gave up because he figured it out. He understood it. He knew it was right. I just couldn't understand it. So that was.
Curtis?
Yeah.
We will put it on this one.
Yeah. No,
that's what Marcus
said. Figure it out.
That's right. Figure it out. Okay. So that's kind of. And there's no comments or questions or anything from out there. It's I think it's a very important piece of this puzzle. And so it's I think it's worth understanding where it comes from. Okay. So then what we're going to do here next is going to do a quick kind of hammering this into this gas condensate blockage E-note is short, just repetitive a little bit. It's kind of giving summary of what we've been talking about yesterday. You'll be tired of it, but you probably won't forget it. Okay, so this is the pictorial of a well that's, now these are actually simulations taking saturation out. You can see this, you know, this blockage region with the mobile oil saturation. I'm not sure what the critical saturation was. Maybe it was 10% or something. So the region of the region 1 is let's say it was 10%. So basically it would be inside this region here is region 1. Then you got region 2. In this case, all the way out to at least to this distance here because it's two-phase. And for vertical wells that are not stimulated, the vast majority of pressure drop is occurring exactly where you have this reduced permeability. Okay? And as you probably should know, as a reservoir or petroleum engineer, that, you know, a damaged skin, a true physical damaged skin, in the first foot only, away from the wellbore radius, you know, it's the worst. It's the worst place to have damage, all right? And what is damage? Well, damage is simply that K, where it's damaged, is less than the absolute permeability of the rock. This is the reservoir rock permeability. Everywhere else, and in the damaged part, it's less. The worst place you can have that lower permeability is where you have pressure. How does pressure vary with radius in a vertical well?
1/r.
It's yeah, velocity is 1/r, but the pressure drop is proportional with logarithm of radius. So we're getting absolutely the biggest pressure drops, dpdr is 1/r, right? So dpdr, so you get the largest pressure drop per inch at the wellbore radius. And that's where you've got the low permeability. So it just makes things all the worse. Okay? And there's the damage skin equation. I think this might have been Hawkins that came up with this. It's basically it's a model. It's if you take the radial model and you say that you have a permeability with radius. Let's see. Let's see. So this is the radius of the wellbore outwards. And then if you say that if this is, we're applying now the permeability here, and you damage this permeability out to a certain distance RD, so you've got a lower permeability and then it becomes constant out here, then this equation for the skin is, if I remember right, it's K over KD minus 1 natural log RD over RW. I think that's the equation. Okay. And this is related to the fact that the pressure drop or the pressure varies with log of radius, and the pressure drop per inch is 1/r radius. And that leads to this. So you don't need a very big damage radius, right? So if this, so for example, if we want to use this as an analogy to blockage, right? Then what would K over KD be? Condensate blockage. What would K over KD be? Well, it would be gas permeability in the blockage region over the absolute permeability. But that's just 1 over the KRG, right? In the blockage region. And the blockage region is that region 1. And we know how to come up with that number because we can calculate the KG-KO ratio. We go to the rel perm curve and we find the KRG. So the blockage equivalent is 1 over KRG in the blockage region, region 1, minus 1. And then the extent of that blockage region, which people asked about, I've refused to tell you how far out it goes. Okay? But if you look at this term here, RW, goodness. RW is what? That's about 0.25 feet. I think if you have a diameter of the hole being 8 inches, then the radius of the hole is 4 inches, and 4 over 12 is 1/3. So it's a little less, a little more than that. 0.3 or something. Okay, something like that. So if we say that the KRG blockage in that article, the monthly article we talked about, that can be as bad as 0.03, and it can go out to maybe 0.3 in a lean condensate for nice rock. So what does this term here become for 0.03? Well, it's 1 over 0.3, so it's 33 minus 1, which is 33, or let's just say 30, okay? So this blockage skin would be about 30 times log RB over RW. 1 over 3, that's 3, minus 1, that's 2, times log RB over RW, okay? So if we just calculate this term RB over RW we start at 1 foot, 10 foot, and 100 feet, okay? Can somebody make that calculation real quick for me?
So the first one is 1.2.
1.2.
Then it's 3.5. Then it's 5.8.
Okay.
What did you say?
So this max is going to be around 30 to 2. 3.5 times 30 is 100. 2 times 7. And 6 is 180. And 18.
No,
16. Okay.
6 times 2.
6 times 3,
12. Okay. So what you see is that you don't need more than a foot blockage region to start seeing what would be potentially significant blockage effect. Okay, and whether it's a relative permeability of 0.03 or 0.3, you need to know it. And if you've got a capillary number dependence that it's 0.03 with no capillary number correction, and it's 0.1 or 0.15 with the capillary number correction, you need to have the correction, because it's a big difference between 2 and 30, the skin. So this is, you can see this, and you can see this, so that's why I basically, I don't care the extent of it. Now, this is using the blockage skin approximation, okay? It's not a great approximation, but it's order of magnitude, okay? It's really this area, this mobility area, that's what you really want to get right. But if you want to look at, as a first kind of just by eye, you can say, well, we've got, this is 100 feet. This is actually a very lean condensate, and I don't know at what time this is being taken from, but it's basically you've got 100 feet of, maybe a KRG of 0.25. Okay. So, this is on the semi-log plot here. This is the pressure gradient that you would expect without any condensate blockage at all. And then you see that this, you're getting much, much more pressure drop. This all being due to the condensate blockage.
This is all region 1.
This is region 1 out to about 100 feet. I don't know what the critical saturation of oil is, but it's like, you know, if it's 100 feet or if it's 150 feet, it doesn't really matter in that long term. It's really the magnitude of KRG associated with this that's important. Okay, any questions about this? So this is the kind of simplified. Yeah, these are Bob's number 0.5 to 0.5, capillary number, if you include that effect. Now, this figure here, this is an interesting figure here because this is a real figure from the Arun field, from the paper SPE 28749. So if you really want to see a good example where condensate blockage was important, this is the go-to paper. And what this is see, the initial reservoir pressure was 5,300 pounds, the dew point 4,400 pounds. So in the first years of production, they were basically not drawing below the dew point probably to get the rates that they needed in the first years. Okay, and then as soon as the flowing bottom hole pressure started dropping below, and that actually what you see is that this drop in productivity starts where the flowing bottom hole pressure drops below the dew point. Okay, the average pressure is still undersaturated, but what they wanted, they thought that all of their models said the productivity index was going to stay at 0.35. That's what their full field model with no GPP option, no blockage scan, nothing. Basically, this was not going to change below 0.35 throughout the whole time. But then when they basically got to this point here, average pressure 4,800 pounds, they started drawing below the dew point. You started getting this loss in productivity due to the condensate blockage effect. So the productivity falls by 50% when the flowing bottom hole pressure drops below the dew point and the blockage starts. So the condensate blockage in this case starts before the reservoir pressure falls below the dew point. This all makes sense. And the more undersaturated it is, the more deceiving it's going to be. Because when you have a highly undersaturated gas condensate, and even the initial flow test may not be below the dew point, you don't see any blockage effect, nothing in well tests, nothing at all. And then if you're going to forecast the effect of it in the old days, before we knew all this stuff, you might run one single well model, but that single well model didn't take into account all of the pressure constraints, probably didn't have a tubing table in it, on and on. It didn't know what the individual well rate was needed to get a certain target field rate. You didn't know any of these things. They just ran a single well model and they got some results, and then they didn't really know how to bring that blockage effect to the full field model, so they just would often ignore it, which is what happened here. So this is a nice example in that reference. I think that reference is probably in the notes here. Here we go. GC papers 20 Arun. There it is. Production performance of retrograde gas condensate, Arun field, Indonesia. Okay. So these things we should have already talked about, hopefully all of them. Condensate blockage is the buildup of liquid around the wellbore, reducing the effective gas permeability and lowering the well deliverability. I don't know what that link there takes us to, but something. Yeah, this is some pictures that Bob put together. This is most of the draw occurring near the well. We've talked about that. This is the oil gas ratio. This is the little RS curve. This is a pictorial of the blockage effect. But here is some simulations, and this tries to answer the question somebody was asking, a couple of people have asked, how does this change over time? Okay. So the first thing, it's a little hard to see with all of these, the start it's hard to see what's really happening close to here. But what you see is that you basically get something that, if you looked at the KRG is lowest for the early times. Okay. And KRG is actually getting a little bit better over time. The distance out of region 1 is basically it's slowly expanding. So that generally won't contract, but the KRG, so the RB is going to be monotonically increasing, but the KRG in the blockage region is going to be getting better. It's going to be increasing over time.
If KRG is increasing and RB is also increasing, then
The RB increases as a logarithm.
okay.
So it's definitely the KRG improvement, because you get producing a leaner condensate. The KR in the region 1 is going to go up. But the best way to answer the question, and probably why I didn't answer it, is that every well field is going to look a little bit different. The extent of the region out here is going to be, you can look at it, but it's not really the main issue. Okay. Point 2, condensate saturations in the near well region can reach as much as 50%, even for a lean condensate, in theory. Okay. Reducing the gas permeability in the near region by a factor of 2 to 20. But it's not the oil saturation that matters, it's the KRG at that oil saturation. Condensate blockage is only important when there is a significant pressure drop between the deep reservoir and the well perforations. That's what we talked about day 1 with that, basically it's if most of the pressures in the tubing, so-called, this is what Fetkovich used to call it, the tubing limited wells. Tubing limited wells, you don't mess with the reservoir. You don't stimulate, you don't do hydraulic fracturing. If it's a tubing limited well, you try to get bigger tubing in the well as an engineer. Condensate blockage is more important for lower KHs. Is likely to be a major issue when a KH is less than 1,000 millidarcy feet, and it's unlikely to be significant for KHs greater than about 10,000 millidarcy feet. And that's because the rates that you can get out of a 10,000 millidarcy feet well, those rates are going to be constrained by either erosional velocity and or tubing size. So the reservoir pressure drop is going to be small. So if it goes from small to not as small, then that's not important. The primary relative permeability relationship affecting the condensate blockage is this function of KRG to the ratio KGKO in the near well region. Saturation does not enter the calculation. The impact of condensate blockage can be reduced by an increase, or the condensate blockage can be reduced by an increase in KRG at high velocities, capillary numbers, in the near well region. Considerable evidence for this effect exists from laboratory experiments and well tests. Okay. So I think this is a good time to just take questions or thoughts, or this is what I knew before I came to the course, which but or just thoughts about this. This is the summary of the effect of condensate blockage.
I have a question about the plot showing the condensate saturation profile over time, which was linked in this first point.
Okay, let me try to find that again. I don't remember.
It was this oil drop.
Yeah. You can
Oh, okay.
These are hidden.
Hmm?
These are hidden.
Yeah, this one here.
This one, yeah.
Okay.
Have you ever experienced, let's call it self-healing behavior? So the condensate saturation over time is not monotonically increasing, but at the later period decreasing again, as we have retrograde condensation and also more lean gas coming from the foremost reservoir, which is able to take again some condensate into gas phase, because that's what we saw in the simulation.
Yeah, so I think what you're asking is, can this region 1 saturation decrease over time? And the answer is definitely yes. It will always decrease over time.
Okay, so there's like a sharp increase in a short of time after we reach the dew point, and then for the later time it's decreasing again.
Yeah, because when the producing CGR decreases from the initial value, then the KRG KRO from the calculations yesterday, if we're always looking at 1,000 psi flowing bottom hole pressure, when you're at limit, so you're at the limit, you're at your minimum bottom hole flowing pressure. If the initial CGR is 200 barrels per million, then at 1,000 psi, that's going to have the highest VRO. It's going to have the highest, the lowest KRG KRO value. Let's say a value of 0.5. When the producing CGR goes to 150 barrels per million, if you take the 150 barrels per million into that equation yesterday, and at 1,000 psi calculate KGKO, it's now 1 instead of 0.5. The KRG KRO is again be monotonically increasing with time because the producing CGR is decreasing with time. So when KRG KRO increases with time monotonically, the KRG has to increase monotonically with time. If the KRG is increasing monotonically with time, the oil saturation in region 1 has to drop with time. So the profile, it's a little bit messy on that one, but so if we're producing if PWF is at the minimum, and that's really when we care about blockage, right? And what you're going to find is that and let's say that happens here. So we only care about what's happening from here. So if the producing CGR, initial producing CGR is here, REI, like that, and so this is going to be dropping down. It drops down a little bit because we're now, the flowing bottom hole pressure went below the dew point here. So we start getting a little bit less RPI, okay? So if you look at the oil saturation in, at 1 foot out, okay? That's going to be doing something like this. This is going to build up. As soon as you go below the dew point, it's going to be 0. It goes below the dew point. This is going to shoot up like that. And then it's going to go like that. Something like that. Maybe it curves up a little bit because flowing bottom up pressure, it's building up like that. Okay, now as this producing CGR drops over time, like that, the oil saturation is going to drop as well. Maybe not as much as you thought it would, but it's going to go down. But the KRG, which I'm going to put in pink, KRG at 1 foot, okay, it starts here at 1, then it barely, then it goes down like that. And it's gonna reach, oh, that's probably too high. So here, this is the worst KRG you're going to get. And then what's going to happen is that this thing is going to go gradually up as the oil saturation goes gradually down. It's going to look something like that. So this is KRG at 1 foot. This is SO at 1 foot. And this is the producing oil gas ratio. All wells are always going to look like this. Guaranteed.
Okay, that's what we also saw.
Yeah, good. That's good. And if you have gas cycling, which we'll talk about a little bit tomorrow, if you have gas cycling, then what can happen here is that if you get gas breakthrough, right, what's going to happen here is that this thing is going to drop off like a rock, like that, okay, when you get breakthrough. And then this thing here is going to go back to your initial no condensate blockage at all. Where you have breakthrough. It's only a function of if the little RP goes to 0 because you got dry gas breakthrough, then you have no blockage effect in the zones where you have breakthrough of dry gas. That's a little ahead of time, but we'll discuss that tomorrow. If you do gas cycling. It's only if the RP totally controls this. Okay, that's the deal. The RP controls it. So if RP happens to go to 0 miraculously through gas breakthrough, then the blockage effect goes away. Okay. Good question. Any other comments or questions?
Maybe another question to beginning of the week, you said that condensate, which is liquid under reservoir conditions, is produced in the tubing as a mist or a film. So that means the amount of condensate, which is liquid under reservoir conditions, the contribution to the total condensate production is rather negligible, volume-wise.
That's right. All of the condensate you put in the tanks is being carried in solution in the gas through region 1 and 2. Region 1 is like a tubing. Nothing's happening. Nothing's being lost. Nothing's, okay, it's like the tubing. So all of the stock tank barrels of condensate you're going to produce is being carried in solution in the gas in region 3 and region 2. Region 3 is single phase. All of it's being carried, most of it's continuing to be carried in solution in region 2. And then thereafter, nothing happens in terms of the flowing composition. Remains constant through region 1, constant through the tubing, enters the separator, and then you get your stock tank barrels.
Some of the condensate is mobile in region 1.
But that doesn't, it's like think of the tubing. It don't matter. What enters region 1 leaves region 1. You don't need to even understand in terms of the recovery. You don't need to understand because nothing's being lost in region 1.
Yes, yes, I agree.
Now, the blockage effect, that's a different thing. But in terms of recovery, the amount of oil that condenses in region 1 is not a recovery issue in general. Now, there's always the exception. If you go to unconventionals, okay, you basically don't have a region 1. All you have is region 2. And you lose a hell of a lot of condensate in unconventionals. Because region 1 never really develops. There's the throughput, the number of pore volumes going through the foot of 1 foot away from the hydraulic fracture through the whole life is you have a hard time building region 1 very far out at all. So most of the reservoir is experiencing region 2, which is being lost. All the condensate is being lost. Okay. So, all right. I think that's the this you've got this blockage skin equation. That's the same thing we just did on paper. Yeah. So basically, you've got same thing we did calculation, and then these single well simulation calculations. An example. These are also given in the GC rate e-note, which I'll actually use instead. It's the same example. So, all right. So that's how are we on time now? 8:30, 15 minutes?
15 minutes for a break, yeah.
Okay. Let's see here. We can get started on this. Okay, so to implement the understanding of the blockage and the 3-region model, we talked about that yesterday, the 3-region model and the use of this rate equation here. Okay, and so what we talked about is, we got a capital S in there. Somebody's in trouble. Should be a little less skin. That's not the blockage skin. This would be damage or something related to geometry, stimulation skin, something like that. So it's well geometry. The main term is KH. We got the well geometry terms and everything here. And this is the same constant that you would need if you replaced for single phase gas flow, if you replaced with just the standard P over mu Z single phase gas pseudo pressure. That always works, no matter what the well geometry. Whatever term here you need to get single phase gas flow right is the same term you need to get the condensate blockage right. Okay. This gas mobility has got 2 terms. The main dominating term is the gas product. This is gas product, should be G hat. This is the gas product coming from the reservoir gas flowing, and this is the gas product coming out of solution from the oil flowing in region 1. And it's really only in region 1 where you have both terms. Okay. This is from the original paper. This gives a little more details for the gas. Just basically where are the numerical constants, field units, and so forth. This is all the three regions, so basically breaking up the integral into the 3 different regions. We talked about that. Yeah. What we have not talked about yet is region 2, the KRG in region 2. So that we need to, that we somehow or another, so let's do that. So region 2, well, we talked very briefly about it. Region 2 gas mobility. Excuse me. First thing is that oil mobility, KRO mu, is essentially 0. So that gives us then the gas mobility is only KRG mu G BG. And so the question is, we need this as a function of pressure, right? And these are, the denominator terms are easy to get as function of pressure. So the question is, how do we get KRG in region 2 as a function of pressure? So that's kind of the question. Oh, goodness, excuse me. Glass of water. In region 2. Okay. So this paper that we wrote, what we recommend doing there as an approximation is that you calculate oil saturation as a function of pressure is approximated by the VRO calculated from constant volume depletion, which is known as a function of pressure, as an approximation. And what you can say about this is it's going to be an excellent, if not exact, approximation at the outer, for the outer part of region 2. And it's going to be okay in the inner part of region 2. Thank you very much. So the reason for it being very good in the outer region is that in that region, you're actually going through a constant volume depletion. There's not really kind of an accumulation, a continual accumulation. There are throughputs of, there's more condensate dropping out in the inner region than the outer region. So, but it's altogether, it's short of trying to use methods that are more exact. For example, using the Jones and Ragavon type or other methods. There's really no, these are very complex, and because the oil saturations are not reaching very high levels, so in this region too, you actually need the gas relative permeability saturation relationship here. And because what we find is that this tends to have this very flat before it drops down. Type of behavior. It goes to zero eventually at some endpoint here. This being the region 2, you're not generally seeing very large drop in the KRG anyway. Plus, it's far away from the wellbore, so the DPDR out there is very low. There's not a lot of pressure change. So that even having the reduced KRG doesn't give you a lot worse pressure drop. So that's the main reason. So getting exactly the oil saturation right in region 2 is not important. It's so important. But the recommendation we give, and that's what's been used, and all the verification work by ourselves and other people who've published on this, that this is an adequate treatment of region 2. So you get, use the CVD curve of oil relative volume. You take that, 1 minus that, and multiply it by the water saturation to get the oil saturation in region 2. Any questions or comments about that? And if it's a lean condensate, don't give it. I just don't care. It has no effect because the saturations are going to be so low. You know, Arun, whatever. The mobility loss in region 2 is absolutely negligible. But if you have a very, very rich gas condensate, then yeah, there could be some effect. And then what's important is to have, you know, to know whether the curve looks like that, or, you know, probably can look like this as well. We've never really seen it looking like that. If it looks like that, you need to know if it's a rich condensate.
The shape of this curve, does it also depend on how you conduct the test?
No. Oh, yeah. Well, in this case, it's not really steady state, but yeah, it should be the way we do the test. You want the condensate coming out of solution. You don't want to be injecting gas and oil at the same time, because in the rock, what's happening is that condensate is precipitating out of the gas. It's sticking to the rock. It's not flowing. So you'd like to have an experiment that is not a displacement experiment, but is a kind of a a condensation experiment. So that's how we recommend doing that. Yeah, so that's a good point. So if you're going to get this one measured point here or wherever it might be, so a single measured KRG at SO less than SOC, and usually at VRO max from the CVD. You do that using a flow test, gas only flow with the oil condensing from the gas. Initially. So what we'll typically do is that we'll charge it like with the original reservoir gas condensate or some equivalent synthetic fill it single phase gas, deplete it down to where you expect the maximum liquid dropout. Okay, and that will saturate all the pores in the core, just depleting, and then we'll flow the equilibrium gas at that pressure and measure the permeability of the equilibrium gas. So you don't get any vaporization of that liquid condensate. That's the best way to do the experiment. Singh can probably give some more details about how that's done and so forth. But so saturate core with original reservoir gas at pressure above the dew point. Usually with connate water. And then deplete to some pressure P tilde, where the VRO CVD reaches its maximum. Or you might pick a pressure, some. And let it equilibrate. Overnight. And then basically flow equilibrium gas at this P tilde to steady state delta P across the core. And that will give you the KRG or the KG. And you'll know the saturation from the PVT of the gas condensate at this bureau of the CVD at P tilde times 1 minus water saturation. So that gives you the oil saturation and the KRG. That 1 point. It's something like that.
This 1 point with respect to oil saturation is important if you have a rich gas condensate. Otherwise,
rich gas condensate only. Yeah, I think that's in that original E note or something. I don't remember. Yeah, basically it needs to be rich condensate. Because lean condensate, the oil saturation will be like 3%. So, it doesn't matter. But yeah, rich condensate may be maximum liquid dropout more than 20% or something.
And the maximum oil saturation that you get in region 1, does it depend on the richness of the gas condensate, and does it matter, or?
Yeah, it doesn't matter. But it'll depend on the rock Relprom curve and the richness of the gas, both. The level of saturation. It'll be both.
Very good.
Hmm?
Break time.
Yeah, so we take a break.
Questions? Questions, Curtis?
Let's see, any questions before we take the break?